as in the header, as well as the measures of variability are also a way of summarizing the data. The next item I would like to talk about is when you have two or more distributions. Let's take, for example, you were teaching a class and you were teaching mathematics to that class. We were also teaching physical science to the same class. And then you administer an exam in these two courses. If the student gets a score of 60 in mathematics and gets another score of 62 in physical science, it will be difficult for you to say in which of these classes has he performed better than other students by just looking at those marks. Obviously, if you're saying performed better, then in the course he has gotten 64, he has performed better than in the 60, the same date. But if we were to compare that student with the other students in the class, then 60 versus 64 may not tell you in which class he has performed better than other students in that class. So sometimes you are supposed to compare distributions in that manner. In fact, most of the statistical questions you deal with relate to comparisons of variables. If you are asking a question to say, if you apply fertilizer to a plot of maize at the rate of 100 kg of fertilizer per acre, and you also have other plots where you are applying 200 kg per acre, then let's say on the 100 kg per acre you have several plots for replication, and the 200 kg several plots for replication. And the question is, which rate of fertilizer is giving you better yields? By looking at one plot versus one plot, it will be difficult for you to make reasonable comparisons. So in such cases, we use the standard scores. Standard scores scores which transform the original scores into one unit of measure. And when you transform them into one unit of measure, then you can easily compare from one group of performance to another group of performance. Standard scores are used for comparing relative positions of one individual in two tests, which is not possible unless those two tests have the same mean and the same standard. standard deviation. So for you to be able to compare two tests, you need to bring them to the same level of measurement. And in bringing them to the same level of measurement, you use the mean and you use the standard deviation. If you have those standard scores, then you can be able to compare relative positions of one individual in two different distributions or two different tests. And one of those scores we use is referred to as a z-score. And a z-score is defined as the distance of a score from the mean, measured by the standard deviation. By the way, the mean and the standard deviation are statistics or statistical indices which you use in a lot of cases. So what they are saying is a standard score is equal to the score minus the mean measured by the standard deviation. That's what we call a z-score. In our in those scores we had there, we had a score for let's use the one we did together. We had a score of 64. Yeah. And we had a mean of 71.2. 71.8. This is 71.2.8. So, if you just take that score of 64, its standard score would be, and what did we find was the standard deviation 11 point, it was 11 point something, yeah? You did go base 11. So that would be the z-score for that score of 62. Which you can compute. 64 minus 78.1. We already found it sometime in the audio. 64. Minus should be minus negative 7.8. Yeah, we got it that time. Divided by negative 5. What does that give us? Negative 7. That's the standard score for 64. Meaning that if those scores, we had 64, 63, 64, we started with 63, 62, 63, 64, 65, 80, 88. actually plotted those scores in a distributed range. Of course, it was going to be this kind of a distribution range. Now, if you put the mean 71, which would have possibly been around there, this is score. The mean actually is always 0 as a standard score. Okay? The mean is always 0 using this formula. Why is it always 0? Since the mean is 71.8 minus the mean is 1.8 divided by the standard deviation. So the probability is 0 divided by 11 point whatever it is. So the mean is always 0 in a standard score distribution. Okay? Which means that this is 0.67 minus 0.67 will go down on this scale minus 0.67. That's where the score of 64 is falling in this distribution. And if you do the same with the other numbers, you must see a standard deviation equals 1.9, 1.9, 1.9.95. Yeah. Let's do a similar thing. We had a score of 52 minus a mean of 60. This is the problem. 52 minus 54, 6. Divided by 1.995. Here 52 minus 54.6 equals what? Minus 2.6 divided by 1.95. Negative 1.3. Here will be the score of 52 falls on minus 1.3. This one minus 0.6 minus 1.3, and it will be going that way. With more scores, we get that way. Those which are positive will be finding going this way. And you can compare. In this case, you will say, if it was one student getting a score of 52 in mathematics and another score of 64 in physical science, comparatively in terms of position in the class, he performed better in physics than in mathematics. Because mathematics is getting much lower standard score than physics. The fact that he is getting negative scores, standard scores, means that he's below average. The one who gets positive scores is above average. Will we make sense? Okay. Let's assume that this score was for student A in mathematics. But this same student A got this score in physical science in the same class. So let's assume the scores we had there were not like that, but the first 5 scores were for mathematics. The last 5 scores were for physical science. And you are trying to compare. And this guy got 52 in the first class and 64 in the other class. So you want to say, in which of these classes did he perform better than his colleagues? Okay? So you compute the standard score in the mathematics class, where he got 52, the mean was 54.6. So you subtract 54.6 from 52, where you got that. Divided by the standard deviation of that plus 8, which was the 1.95, giving you the standard score of 1.3. In this other class, he got 64, but the mean was 71. So 71 minus 64 minus 71.8, you get which is 7.8, and 7.8 divided by the standard deviation of that class, you get 0.76. So it means that he performed better in this class. Than this class, because the majority of his colleagues in this class are above him, whilst in this class they are below him. Okay? So the standard scores are basically used for you to compare position of an individual in comparison to others in 2 tests, 3 tests, 4 tests, whatever. You will hear about the correlation procedures, where you correlate one variable with another variable. But for you to do correlation, you actually use the standard scores. This making sense? So if with those this formula which we have used there, one standard deviation above the mean is always equal to 1. So here, there we have two standard deviations. We have used the standard deviation of 11 point something. We have used the standard deviation of 1.9. In whichever case, that standard deviation in standard scores becomes 1. And the mean is always equal to 0. And therefore, you can directly compare the scores without problems. Scores from 2 distributions can be compared equally because of this characteristic that the mean is always 0, the standard deviation is always 1. So you can convert the original scores to these scores, and you can be able to compare performance in any different type of distribution. Questions? I'm seeing you looking in the air. And I think that somewhere I've lost you. Where? Yes, sir. Are we in the same boat? Zubeka? Did we know it? You can, sometimes you'll find people change from using the Z-score, the small letter Z score, representing standard scores, to a capital letter Z score, representing standard deviations but with a convention. In this distribution, it's the same as that one, but what they do is to change the mean. Instead of it being 0, it should be 50. And the standard deviation, instead of it being 1, they just put it to be 10. The reason why sometimes they use that is, imagine what you are describing. What is your name? First name? Godwin. First name, sir? Yeah, okay. Imagine you are describing John's performance in classes. Then you are saying his performance is minus 1.3. This is a bit of news. Minus 0.6. So to avoid the negativity associated with the minuses, we convert that formula into that formula so that all the numbers are positive. So in this Z-score, anybody who gets a Z-score of less than 50, is below average. Anybody who gets a Z-score above 60, above 50 is the above average. But it is the same as this one, simply because we don't want to be describing people in terms of negatives and positives. We want to be describing people always in terms of positives. Any questions about that much? What is the standard score? Ndio si mwakifuza mafuso. Ndio kakauli si mwakifuza mafuso. Nende ndio kufuza. What is a standard score? And why do we worry about the standard scores? I'm saving my battery here, which means these numbers are going to go in. So standard scores are original scores in a distribution converted or standardized by using the standard deviation and the mean. The standard score is the I am coming, sir. Is the distance of a score from the mean measured by the standard deviation. So that's the definition of the standard score. The distance of the score from the mean as measured by the standard deviation. And that's what we were doing there. Measuring the score, the distance it is from the mean as measured by the standard deviation. You can say the same by simply saying the deviation score divided by the standard deviation. Why do we need to have a standard score in statistics? Why should we bother ourselves computing a standard score? It's beautiful stuff. Yes, sir. 8. Standard scores help us to be able to compare positions of individuals in different tests. To compare positions of respondents in two variables. And I was saying that the correlation, which we'll be talking about next week, is one of the statistical procedures we use for comparing variables. And very often, a procedure which you want to do in order to describe your sample, in order to describe your population. But to do so, you need to compare the scores into standard scores, and there you can be able to compare easily how those scores are deviating from each other in the original measure. The question, why should we bother ourselves computing standard scores? What is the use of standard scores in statistics? And I say standard scores are used for comparing performance in two tests, for comparing positions in two distributions. Comparing performance in relation to others in two tests, comparing positions in two distributions. If, for example, you had a question to look at a person's physical strength versus age, and we're arguing that as people grow old, their strength changes. That would imply comparing it. So if you came to University of Lilongwe and picked the 50 students and asked their age, how old are they, and you recorded their age. And for each of those students, you ask them to throw a stone with the intention of seeing how long this stone cover, what is the distance, assuming that their ability to throw the stone represents the strength they have. So you ask all these 50 students to throw a stone and you measure the distance that stone has covered. At the end, you want to compare whether the distance the stone covers is related to the age of the student. Maybe one assumption is as the students grow old, their strength increases. So as the students get older, the distance the stone covers will be longer. The younger, the shorter the distance. But for you to be able to say that, you need to compare, to correlate the two variables. To relate the age with the distance covered. And the best way to do that is to convert the age into standard score measures and also convert the distance covered into standard score measures. Then you can compare very well without problems. Okay? And there are many situations where in statistics you have to compare two variables, how they relate to each other. Some variables, as one variable increases, the other one increases. In some cases, the variable increases, the other one decreases. Actually, in this one about the age strength, from at the younger age, take primary school kids, the older they grow, the more distance they will cover. But when you get to my age, the older they grow, the shorter the distance they will cover. So in one case it will be negative relationship, in the other case positive relationship. But for you to do that, you need standard scores. Is it making sense? Okay. I think we'll start from there next time. Nice weekend. Of course, I'll give you an exercise on this one so that it also makes sense, just like we did with the standard deviation. How are we doing? Is this making sense? Or we are just confusing one another?
then we should sit down and study the program.